All right, we all know quantum mechanics is, well, it's weird. It tells us that deep down the universe is all about probability and chance. But what if that's not the full picture? What if there's a secret layer to reality, a hidden reality where nothing is random at all? Let's dive into that idea. This is the central question, the one that could change everything. What if all that randomness we see in the quantum world, what if it's just a trick? A kind of illusion that's hiding a much deeper, more predictable order underneath it all. So this really sets up two completely clashing views of reality. On one hand, you've got the standard view, which basically says the universe is a cosmic casino. It's fuzzy, it's all about probabilities. But on the other hand, this alternative idea, pilot wave theory, says the universe is actually more like a perfectly crafted Swiss watch. Everything follows a set, predictable path. We just can't see all the tiny gears turning. Now, this idea of a predictable, deterministic universe isn't just some wild guess. It's a real, fully formed theory. It has a pretty fascinating history, and it suggests there's this hidden layer to reality that brings a beautiful order to what we thought was quantum chaos. It's called pilot wave theory. And the core idea is actually pretty simple, but it's totally revolutionary. It says that particles, like electrons, they aren't just these vague clouds of probability that are everywhere at once until you look at them. No, instead, they have a real, definite position at all times, and they're guided along their path by something called a pilot wave. And you might think this is some newfangled idea, but it's not. This concept was first dreamed up way back in 1927 by Louis de Broglie, one of the founding fathers of quantum physics. It got a bit lost for a while, but then it was rediscovered and polished up by the physicist David Bohm in the 1950s, and today it's still a really active area of research. Okay, so how does this guiding wave actually work? How can it possibly explain all the quantum weirdness we see in experiments, like how a particle seems to be in two places at once? The logic here is surprisingly elegant. First, and this is a big one, every single particle always has a real, specific location. Period. Second, there's this guiding pilot wave. Here's a good way to think about it. Imagine the particle is like a tiny cork floating in a river. The wave is the current. It tells the cork exactly where to go, and the result? A perfectly predictable path. The particle isn't behaving randomly at all. It's just following the flow of its wave. This is the key insight. You'll hear physicists talk about a hidden variable in this theory, which sounds super mysterious, right? But it's not some exotic new force. The hidden variable is simply the particle's actual position. It's always there, it's always real, and it determines everything that happens next. We just can't measure it without, messing up the whole system. Okay, now hold on, because this is where things get truly mind-bending. Bringing this kind of perfect predictability back to the universe comes at a very strange price. It forces us to accept a concept that even Albert Einstein found deeply, deeply disturbing. So, if this one pilot wave is guiding every particle, and if that wave can be spread out across vast, vast distances, what does that imply? What's the shocking connection between all those particles? It implies something called non-locality. This is the idea that two particles can be linked, connected, even if they're on opposite sides of the entire universe. And what you do to one can instantaneously affect the other. This is the spooky action at a distance that famously bothered Einstein so much. And pilot wave theory doesn't just allow for this, it absolutely requires it. So how does this instant connection work? The theory calls it the quantum potential. Now, this isn't a force like gravity or magnetism. It's better to think of it as a kind of information network that connects absolutely everything in the universe through that pilot wave. If you poke a particle over here, the wave instantly updates everywhere. In this view, the universe isn't just a collection of separate little things, it's one single deeply interconnected whole. So, if this theory gets rid of randomness and explains all the quantum weirdness, why isn't it the standard model? Why aren't we all taught this in high school physics? Well, it has its own problems. Let's put the theory on trial and see how it holds up. And when you put the two theories side by side, the differences are just stark. Pilot wave theory is deterministic. Particles follow real continuous paths. The standard Copenhagen view is probabilistic. There is no path until you look. But here's the crucial difference. In pilot wave theory, when you make a measurement, you are simply revealing a reality that was already there. In the standard view, the very act of measurement creates the reality you see. These are two totally different philosophies about the world. But yeah, there are some pretty big challenges. That spooky non-locality is a really tough pill for many physicists to swallow. I mean, an instant connection across the universe seems to break Einstein's cosmic speed limit, the theory of relativity. On top of that, the math behind it can get way more complicated than the standard model. And those are the main hurdles that have kept it out of the mainstream. But here's the twist. Despite all the philosophical arguments, the theory is actually really practical. Because it treats particles as having real paths, engineers and scientists can use it to model exactly how electrons move through new kinds of materials, or to simulate what's happening inside tiny nanoelectronic devices. So even if it's not the final answer to everything, it's an incredibly powerful tool for building real-world tech.
And all of this brings us right back to the core of the debate. Pilot wave theory really presents us with a profound choice. A choice about the very nature of the universe we live in.
This is the ultimate trade-off. It's the big choice on the table. Do we live in a universe that's random and local, where everything is fundamentally separate? Or do we live in a universe that is predictable and perfectly ordered, but one where everything is deeply, non-locally, and, spookily connected across all of space and time? The wildest part is that right now, both of these theories make the exact same predictions in experiments. Science can't yet tell us which one is right. The choice is, well, it's philosophical. So I'll leave you with the same question we started with. Is all that quantum randomness real? Or is it just hiding a deeper, more predictable, and strangely interconnected reality?